Thermal processes, the role of conduction, convection, and radiation in everyday life, by me. So, a brief introduction. Energy transfer takes place constantly in our universe. It's what goes on in the center of our sun in order to create light and create new atoms, new elements. It's what drives biological processes here on Earth. It's what heats our food. It's what keeps our homes warm in the winter and cool in the summer. There are three thermal processes: conduction, convection, and radiation. And each of them are critically important to our way of life, the way that we do things. And not just our lives, but every living thing's life. So let's get into it. Let's start with radiation. What is it? Well, radiation is energy that travels in the form of electromagnetic waves that have energy and momentum, but no mass, and do not require a medium to propagate. So waves have energy and momentum, obviously, but no mass. Because they're moving, they have energy, kinetic energy. They have no mass. Photons, if you think about photons are just pure, straight up energy. They don't need a medium. We'll talk about convection later. That needs a medium to propagate, to work. It needs to be in a fluid. Conduction needs contact in order to cause transfer to occur. Radiative heat is given off in the form of infrared light, which is one of spectra on the greater electromagnetic spectrum. So the electromagnetic spectrum is basically light. That's all it is. Light is the electromagnetic spectrum, and electromagnetic spectrum is light. We're going to talk about that in a second. So if you look in the bottom right, this is somebody's hand. And every living thing, especially like mammals or warm-blooded creatures, give off infrared radiation. Why is that? Well, because we have biological processes taking place in our body at all times. If you think about the average internal temperature of a human, it's around 98 degrees Fahrenheit, and that's a healthy temperature. Her hand is warm relative to her environment and giving off infrared radiation, which we can take in using a special camera as light and take a picture of it. So this is the electromagnetic spectrum that I talked about. Very, 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 very important. There are many wavelengths, and they're all sort of divvied up into different sections with different properties based on their energy, which is based off of their frequency. And that has their frequency is an inverse proportion to the wavelength. F equals 1 over, I believe, gamma, and where gamma is the length of the wave. So the three with the lowest energy are radio waves, microwaves, and infrared. Radio waves are what we use in order to send information through your radio, hence radio waves. Microwaves vibrate water molecules in your food and heat them up in your microwave. Infrared, just talked about that. We give off radiation in the infrared spectrum. Anything that has heat is giving off infrared radiation. So infrared is at the very bottom of the visible light spectrum, more towards the red. If you look at the visible light, it goes from 4 times 10 to the 14th hertz to 7 times 10 to the 14th hertz. More energy than radio waves and microwaves and infrared for the most part, but not harmful. It's what we use to see. It's what hits our eyeballs and gives us a picture of the world. The three with the highest energy are ultraviolet, X-rays, and gamma rays. Ultraviolet, we'll talk about on the next slide, can potentially be dangerous. X-rays, even more dangerous than ultraviolet, but we use those to see bones. They go straight through us. Gamma rays are horrible. They're terrible, terribly dangerous, and could ruin us if we're exposed to them for even a small amount of gamma radiation. Imagine the Hulk. He was exposed to gamma radiation for quite a while, and look what happened to him. Examples of electromagnetic radiation. So much of all electromagnetic on Earth is received from the sun. It's the main source of light on our planet, for obvious reasons. The sun's rays warm the Earth's surface with infrared radiation. We see the visible light produced by the sun, but those aren't the only things. Those aren't the only wavelengths that hit our planet. UV light also hits our planet, ultraviolet. There are 3 types of UV light, none of which are good for us. But UVA is the least energetic of these 3 UV types, and it causes sunburn. UVB is somewhere in the middle. That can lead to skin cancer, and UVC could potentially cause much worse things. But luckily, we have an ozone layer and an awesome atmosphere looking out for us, and it reflects most of that light back into the cosmos. The next thermal process is convection. Now, convection is important because it warms our homes, warms our lakes and ponds, which leads to microbial growth in those small ecosystems, which feeds fish, which feeds us. Convection is extremely important. Unlike radiation, heat transfer through convection occurs through the medium of a fluid, as I mentioned earlier. It's a cyclical process, meaning that it occurs over and over and over again in a cycle. It occurs in which the warmer, less dense parts of a fluid float to the top of a system, then cool down, become dense again, and sink back to the bottom, where the process is repeated again. So once it sinks back to the bottom, near presumably a heat source, it warms up, goes to the top of the system, cools down, and it sinks back down. And this happens over and over and over again. So molecules in a fluid at a certain temperature have a specific density. This is what's going on a molecular level. We know about light. It's a particle, it's a wave, we don't know. But in a fluid, we know there are definitely particles, they're not acting weird. We know what they are for the most part. If you just take some water, we know what's in there. It's H2O. So we know that molecules in a fluid at a certain temperature have a specific density. When heat is added, it excites the molecules, and they begin to slip past one another faster and faster, increasing the distance between them. This causes a decrease in density. Increase in velocity, increase in molecular velocity means increased distance between them. This allows cooler, more dense molecules to float to the bottom between those spaces, and then that starts to warm up near the heat source again, floating to the top, and then repeating the process over and over again. So some examples: radiators in houses, those big white things, they take in cold air near the bottom and heat it up, which causes it to rise to the top of the room where the radiator is in, where it will then cool down after a period, sink to the bottom, heat up again, and this keeps happening over and over again. Convection also takes place in the Earth's crust with rock. So, well, what the heck? Rock's not a fluid, it's pretty solid. Well, actually, at the core of our planet, it is so hot that rock melts. It literally turns into a fluid, and it gets hot near the bottom. Guess what? Expands, rises to the top of this fluid system, cools down again, turns into the rock that you and I see on the crust of the Earth, and some of it will sink back down, heat up, and this process will occur again and again. This is what causes the tectonic plates to move and smash into each other. It's what causes this upwelling effect, which pushes up and moves a tectonic plate into another one, either forcing it to subduct or be the subductor, forcing this guy under. And that's where places where subduction occurs is where mountain ranges form. It's where earthquakes occur most often, on those tectonic plates where they're smashing into each other, and it all has to do with the basic thermal process of convection, which occurs in your home, just as simply as that.